Hello, geology enthusiasts. We are back for another exciting episode of Geologic Time. So grab your caffeinated beverage and let's get started. So today we're going to focus on the excitement that is the Devonian period, but let's reflect a little bit to where we have been in the past couple of geologic periods, because again, we're trying to put this in the framework of a story. And so what we said was we came out of the Ordovician from 485 million years ago to about 443 million years ago. So a geologic period lasting about 41 million years. And when we entered into the Ordovician, remember that we were coming out of a major glaciation called the Varangian glaciation. And so climate was beginning to warm. And what we talked about within the Ordovician is that it was some of the highest overall sea levels that we saw on the planet. So sea level was considerably higher than what it was today, according to Walther's law and the worldwide sea level curve. And so that provided many new ecological niches. And within those ecological niches, remember that they were mostly developed in the shallow marine environments. So what came online was an increase in phylum Brachiopoda, an explosion of phylum Bryozoa, and remember that we even see initial organisms in phylum Chordata, so developing the very first vertebrates on the planet. And the exciting news really of the Ordovician was the development of Nautilidea. And Nautilidea was a giant predator. So remember that it looks like an ammonite, but it has a diameter of about 8 feet across. So this giant predator, and that giant predator was able to have mobility, but more than that, it was able to regulate itself within that water column. So it was able to regulate where its position was based on those buoyancy chambers. So it could be at the top of the water column or looking for prey, or it could be at the bottom, resting. So it was a great advancement. And we talk about developing one of the very first food webs in the ocean. So we have very basic plankton, and then we move up to scavengers, and then we move up to some very top predators. So the complexity between Nautilidea and trilobite, which we saw uprise in the Cambrian, is significantly different, with Nautilidea being significantly advanced with its buoyancy chambers and eyes and size and predatory skills. So I always find it good. What we've learned in historical geology is that all good things come to an end, and we ended the Ordovician in a mass extinction. And not only was it a mass extinction, but it was the second largest mass extinction that we'll find in the geologic record over the course of 4.6 billion years. So that was sad, because Nautilidea, extinct, never to be seen again in that capacity in the fossil record. Half the phylums of Bryozoa and Brachiopoda are going to also go extinct. And so the reason why we went to the mass extinction in the Ordovician is because the climate began to change. And so Gondwana land was heavy at the southern end of the globe. It was, those land masses were circulated by cold water. And so once you have the initial formation of a glacier, it can easily perpetuate itself in a positive feedback cycle, which is called the albedo effect. So what we see by the end of the Ordovician is a drastic decrease in sea level. So we see a 165-foot decrease. So we're moving into a regressive boundary as that water on the planet is being trapped in the glaciers. We notice that worldwide by looking for an unconformity that we find in the fossil record. And essentially what's happening is that those oceans are becoming anoxic, so environments without oxygen. So the majority of life living in those, remember by definition, we talk about a mass extinction being at least 80% of life on the planet dying, and we see that at the end of the Ordovician. So moving into the Silurian, instead of focusing on the shallow marine environments like we've done for the other parts of the Paleozoic, now for the very first time, because of that regressive boundary, we get to focus on land. And so we see the very first uprisings of kingdom fungi and kingdom Plantae. So when we talk about geologic time, and when we started our journey, we introduced those 5 different kingdoms. So in order of complexity, we said Kingdom Onera, Protista, Fungi, Plantae, and Animalia, so listed in order of complexity. But that's different than what we see the uprising in the fossil record. So instead, in the fossil record, we see first Kingdom Onera, Protista, Kingdom Animalia, and then it's not until the Silurian that we see the formations of Kingdom Fungi and eventually Kingdom Plantae. So the beautiful thing about the introduction of those 2 kingdoms on land is that we are now developing different ecological niches and different habitats for other things to live beyond those shallow marine environments. So with Kingdom Fungi, that fungus is going to first grow on rocks. What we learned about rocks is that they contain minerals. Those minerals are going to provide nutrients for the fungus to live. So they are essentially breaking down the bedrock into soil. And so then we can see signatures of first non-vascular plants like mosses that are able to have microbial roots, and they develop laterally. And then as the soil becomes richer and deeper, we're going to see the uprising of vascular plants. And vascular plants are going to be truly successful and also provides a positive feedback cycle. So vascular plants have a root system that can dig deeper, and they can grow taller as a result of having transportation systems called xylem and phloem. So they're able to transport both water and nutrients to leaves. And so we're going to see the greenery developed in the vertical capacity and also the horizontal capacity. So with root systems, you're able to encourage the breakdown of bedrock more, and you're going to have more and more soil that begins to form on the planet. So the very first, what we call paleosols, ancient soils, paleo means ancient soils on the planet. The very first signatures of those, we see them in the Silurian. Prior to that, it was just bedrock, and that bedrock was mostly underwater for long periods of time. So within those vascular plants, one of the things that we see is a lycospid, and a lycospid is kind of like a softwood palm tree, but it's able to grow about 100 feet in tall. So again, developing these different ecological niches. Once soil begins to form, we start to see arthropods, and we've already developed phylum Arthropoda when we saw the first signatures of trilobite in the Cambrian, but now we see on land examples of that. So we start to see millipedes and scorpions, and we find those in the fossil record. And those too are going to aid in the development of soil and also act as food for other things that are going to develop. So we move out of the Silurian and we move into the Devonian. And so the Devonian is going to be about 419 million years ago to about 359 million years. And within the Devonian, we can look at the picture that's on the screen. Again, Gondwanaland is at the southern end of the globe, but it's moving north. And so even portions of it are now headed towards that equator as we're moving towards our Pangea cycle by the middle of the Triassic. So it's moving more and more towards the north, and the amount of land that's above sea level is going to increase, and it's going to increase with mountain building. So we're going to start to see some collisional effects that develop elevation on the planet that we haven't seen prior. And another interesting thing that we see on the planet for the first time is this idea of an epicontinental seaway. And an epicontinental seaway is one that is a body of fresh water. So if you take a look at the map and you find the location of North America, you start to see some epicontinental seaways that move up to places like Ohio and Michigan. So these internal seaways that are freshwater. Prior, when we talked about those shallow marine environments, we were only talking about saltwater type of environments that had an increase in salinity. And so here we're seeing something new, and that's going to lead to some interesting changes on the planet. Here's an example of what North America might have looked like. again with the epicontinental seaway, but other than very small portions of the northern Appalachians being above sea level, we don't see much of our land exposed. So you're thinking in terms of shallow marine environments, and these shallow marine environments are going to be mostly fresh water. So we can look for those signatures. So remember, as we went through the Ordovician, and the brachiopods and bryozoans took a big hit. What we're going to begin to see rebounding are those different families and orders. And additionally, like stromatolites, they always receive devastation, but they always begin to rebound back. And so that is going to be the formation of building up those shallow marine environments. So things that were once there are going to quickly rebound. The beautiful thing about the Devonian, and you should write this down, is that the Devonian is called the age of fishes. And so we're going to see an explosion of phylum Chordata that we just saw very primitively in the Ordovician. And this is our first example of that. So within phylum Chordata, we start to define a class that's called the ostracoderms. And ostracoderms are these jawless fish. And what's different than the jawless fish that we saw initially in the Ordovician is that these are starting to have armor. And so that was an advancement that we saw in the Ordovician with Nautiloidea, that it grew substantially in size, but it also grew in armor to protect itself, as did the trilobite, right? So in the case of the ostracoderm, we start to see these bony plates that began to protect themselves. Ostracoderms do not have paired fins, and they don't have jaws. So you're considering these guys probably to be scavengers, eating phytoplankton, eating remnants of what's in the water column, and they're probably not all that good of swimmers. At least they're not going anywhere too fast. And when we look at ostracoderms in the Devonian, these are going to be just in freshwater environments. So at modern day, we can find examples of ostracoderms. Do you know any modern examples of ostracoderms? I don't think these are so popular in the South, but certainly we find these up in the North. And a common modern example is called the lamprey. So if you take a look at the fish on the screen, the lamprey are the black things that are hanging off the sides. Not exactly leeches, but kind of along that lines. And these are really common in the Finger Lakes in New York State. I've seen them there, unfortunately. So when you look at the mouth of the lamprey, you can kind of understand that it does not have a jaw. So it's kind of just a filter feeder. It doesn't have paired fins, and oftentimes they're parasitic. So they have to have a host in order to be successful and to have mobility, because they don't have fins and are not considered to be all that good of swimmers. So for fun, sometimes if you're ever on a geology field trip and you find a lamprey, you can horrify your friends, just as my friend and colleague here, Matt, often did. So phylum Chordata and the ostracoderms. Now we move into a class called Acanthidans. And so we start to see some of the very true fignosers of fish that we know on our planet today. So moving up again in complexity, and that's a theme that we're seeing throughout geologic time. When we look at an Acanthidian, this is the very first fish that has jaws. Now the jaws are not going to have complexity. It's going to be a primitive jaw. And in fact, when we look at the skeletal record of these, and we have very good skeletal record of fishes, because they do have a vertebra that's made out of cartilage, and they make for very good signatures of impressions in the fossil record. So we have a very good understanding of what the exterior looked like. So impressions of their outer structure, their gills, etc., and then also of their interior if they are preserved differently, right? So Acanthidians have this primitive jaw, and what that means is that the jaw is not attached to the upper jaw. So it's called a floating jaw, And so that floating jaw has muscle mobility, but they're not going to be a predator. Like these fish are successful, but they're not going to be as successful as other predators that we'll think about in sea uprising within the age of fishes. We see paired fins, as I mentioned, and we also see scales, and those are going to be features that are going to be passed on to later groups. So as we look at these structures, remember that we're thinking in terms of Darwin's ideas. So like the idea of natural selection, so features that help you become more successful in the natural environment. We think in terms of those being genetic changes that happen over long periods of time. So the Devonian is more than 20 million years of advancement that can happen. And then we can see how those changes adapt or not compared to what is happening in the natural environment around them. So we're thinking in terms of vestige structures, you'll remember, and in terms of homology. So once we have acanthidans, we are going to think in terms of developing a major predator. And what we've seen in the Cambrian is the major predator was a trilobite. The major predator in the Ordovician was Nautilidea, and we are setting the stage for the next major predator, which is also in Phylum Chordata in the class called the placoderms. And so the placoderms, common name for what you see on the screen, is called dunkleostasis. If you ever make it to really pretty much every natural history museum that I've ever been to have a model of dunkleostasis representing the biggest and baddest fish to dominate the Devonian oceans. Like this is the guy. This is the top predator. Most of the time, however, dunkleostasis is only found in those epicontinental seaways. So it was a freshwater dwelling fish. So can you imagine going to Lake Michigan and throwing your fishing line in and reeling in a dunkleostasis? These guys are massive. So they are going to be more than 20 feet in length. Their head cavity is complete armor. So when we look at this picture on the screen, it is completely bony. Significant eye cavities, a big brain cavity. And another great advancement is it's got this dermal bony plate to protect its head and gills. So that is a large advancement. And there's a lot of discussion as to why dunkleostasis has such significant features to protect them from other predators, because there wasn't any other predator. Dunkleostasis was the top predator. But what's interesting is when paleontologists look at the dunkleostasis record, it appears that they might have been carnivorous. And so you've got this massive creature that's got to eat a lot of food. And obviously it's meant to fight, because you can see how these lower and upper jaws are serrated. So very different from the ostracoderms and the acanthidans, because this thing is meant to be a top predator. And of course it's preying on those two groups for food, but looking at the fossil record, it might have been carnivorous. And so when you look at the skeletons, you can see serrations on head cavities and body parts of the dunkleostasis as they might be fighting or trying to combat one another. Upper jaw and lower jaw are fused or hinged together. That is going to be greatly successful, obviously. And they are just massive creatures, and their common home is in Cleveland, Ohio. So many of the dunkleostasis that we have in museums are found in Cleveland. So these shallow marine environments are going to be homes to dunkleostasis. I'm going to put a video on the website for you that's called A Tribute to Dunkleostasis. I think you'll really enjoy seeing what he is perceived to be in his natural environment during the Devonian. Okay, so Age of Fishes is known as the Devonian. The next and maybe most important group in the Devonian is called the lobe-finned fish. It's also referred to as the lungfish. So here's a schematic on the on your screen. The cool thing about the lungfish is that they're still around today. So we can learn an awful lot about the lungfish. The present is the key to the past, right? And the past is key to the present. So there's about 3 genera that are present today. And I was lucky enough to be able to be on an Amazonian expedition where we caught some lungfish. So we're talking massive creatures, like we're talking more than 6-8 feet long, just massive in size. And so the thing about the lobe-fin fish, or also called the lungfish, is that it starts to develop its swim bladder into lungs. So all fish have a swim bladder, and that swim bladder, similar to Nautiloidea, allows them to regulate themselves in the water column. And remember that fish, like we've talked about in phylum Chordata, so the acanthibia, the ostracoderms, the placoderms, they are all respiring through the water column with gills. So they're taking in oxygen from the water column and processing it through their system using gills. What's different here is that the lungfish, portions of its swim bladder develop into a true lung. So they are an advancement over all of the other fish that we have seen up to this point. This schematic just kind of illustrates that for you. The swim bladder muscles relax, they get bigger, the fish is lighter, so it floats. The bladder and the muscles get smaller and they have less weight, and so they sink. And so that swim bladder is, again, just like regulating them in the water column. So a portion of that is making its way to lungs. So when we think of a lungfish has gills to process the water, but it's also developing a true lung. Here's a picture of it at modern day. This is a small one compared to what many of them look like, but they're very similar to what we find in the Devonian record. So the top is an example of a lungfish that was found in the Devonian record, and below is a modern day example. So again, we are thinking in terms of building up these in the fossil record and learning about what we know about them today. This is a picture from the Tennessee Aquarium. So if you ever make it to the Tennessee Aquarium, you should take a look for these. I don't think I mentioned this. These are freshwater epicontinental seaway species. So we don't typically find lungfish in saline environments and ocean conditions. These are found in freshwater conditions, like the Amazon River, as an example. So that was in the freshwater aquarium in Tennessee, that picture. So the big buildup here is thinking in terms of how that lungfin fish can develop and contribute to the uprising of amphibians on the surface of the planet. So remember, although we're focusing on, and we call the Devonian the Age of Fishes, remember that there's still land exposed because of the big regression that happened at the end of the Ordovician. And remember, during the Silurian, we built up that land. So we're thinking about how are we going to transition from these water environments onto land? Because that land is just, it's waiting. It's a new environment that is devoid of life. And so we need to figure out how we're going to get to land and how we are going to go through adaptive radiation to get to where we are today. So we've talked a little bit about transitional life forms when we talked about principles of homology and vestige structures. So let's kind of review that as we looked at this schematic on the screen. So what we're seeing on the top is the lobe-fin fish. And so in that diagram, it's showing you how the fins are holding parts of a radius, an ulna, a shoulder cavity. It's showing you where it might have a pelvis, a femur, and then the fibia and tibia. So when we look at the geologic record, we find something that's called the transitional species. And the transitional species is the smoking gun that links that lobe-fin fish to the amphibian, and that is called the Ichthyostega. So Ichthyostega is the transitional species that we find in the fossil record, and the transitional species means that it has both the parts of a lobe-fin fish, but it also has parts of the very early amphibians. So prior to finding Ichthyostega in the fossil record, it was only a guess as to how fish moved into amphibians. So this filled in a fantastic geologic gap. So by finding this, it became really exciting because this was the smoking gun that we needed to link and confirm that fish moved onto land via a transition. So Ichthyostega then is shown here on the bottom as an early amphibian. And so it has, remember the lobe-fin fish was transitioning its swim bladder into a true lung. So an amphibian has a true lung, right? So amphibians need water to reproduce. So they're still linked to water. They can't go too far because they need the water to reproduce and their skin will desiccate, but they have to have the capacity to breathe on land. So that's the advancement. Fish have gills, amphibians have true lungs. The lungfish help to develop the transition between those two. The present is the key to the past. We understand and can find lungfish on our planet today. And so we were able to study them. Then we find this in the fossil record to confirm. So Ichthyostega then has a true lung, and then it also has retained the fish-like vertebra. And what's interesting is that when we think of a fish for sure has a rib cage, but that rib cage is developed to be in an aquatic type of environment. So the other advancement that we see that makes the amphibian successful is that they develop a truly supportive rib cage that allows them to be under gravity, right? So they have to have the pressures of gravity that you don't necessarily see when you're underwater. So developing a true rib cage, and then they are still going to be tied to water for reproduction, and certainly they can desiccate. So amphibians, right? You're thinking in terms of like frogs. And so Ichthyostega is a very primitive type of frog that we start to see. Here's a replica with its gills, and you can look at that interesting like tail-like structure that it retained from being a lungfish. So when we think of amphibians on the planet today, they don't necessarily need fins, and so that's going to be something that is going to dissipate with advancement. It's got that a long and narrow body that would be closer to a lungfish, allowing it to move in the water column. Its feet are still webbed, and what we're going to see is that's going to eventually dissipate over time. So this recreation gives us an interesting look at what Ichthyostega might truly look like. And here's a picture of that respiratory system. So the first one shows you how the lungfish is, how that swim bladder is transitioning between a lung and the gills. And so you're processing both the oxygenated blood and the deoxygenated blood and how they go through this mixing pattern. And then it shows you the capacity of an amphibian using just a lung. And so you have atriums now, right atriums and left atriums and aorta valves. And so the circulatory system is going to be different because you're only taking in air from the surface, right? So you're able to take in air, and what happens when you take in air, if you're in, you're going to then respire carbon dioxide. Other things that have been identified with this transitional species is that there's a whole lot of similarities in tooth enamel between lungfish and amphibians. When in that picture, the replica of the Ichthyostega, you saw how it had teeth, and so we can look to the teeth enamel to give us some clues. And that's something that we often do, remember, because when we think about teeth and fossils and fossil preservation, the durability of hard parts. So teeth are something that we can commonly find in the fossil record, and so we look for that as an indicator. And so there's a connection between that. There's similarities in the skull, remembering that the upper cavity is usually more preserved than the lower cavity, and there's similarity in their limbs. And we saw that in the first schematic. So that's kind of your principle of homology, is that all things within kingdom Animalia have the same bony parts, but perhaps they have a different or similar function. And then with the vestige structures, when we look at Ichthyostega, we look at that long tail that looks like a fin. Eventually that will dissipate because it won't be useful. And then the webbing on its hands and feet will eventually dissipate because that's not going to be useful because they're not swimming so much in the water column. So Ichthyostega, and I'll put up a little video so you can look a little bit more about Ichthyostega and appreciate Ichthyostega because it's a fantastic thing in the fossil record for sure. It's fantastic because it helps us to answer some questions about why fish move to land. So I want you to think about that for a second as we pose this question on the screen. Why did fish move to land? What do you think? I kind of gave you the answer already. Why did fish move to land? There's 3 different reasons, in fact. Did you come up with something? Good. You guys are smart. So the first thing that's happening is that remember that Gondwanaland is moving closer towards the equator, and so more and more land is being uprose above sea level. So especially those epicontinental seaways, those are going to begin to dry out. So the less water there is on land, the more crowded your environment is, because what happened in the Devonian, we developed all these different types of fishes. So the oscoderms and the acanthidians and the placoderms, are giant. And so the environment of which they're living is becoming crowded. And that was a principle that Darwin talked about, right? So remember Darwin was looking at the Galapagos Islands, and there's 13 islands, and he suspects that after the island that was close enough to South America, once that got too crowded, the bird was like, I'm out of here. And he went to look for another island. And he found one that was relatively close. And he's like, hey, I've got all this space. I get to adapt. And so here, there's going to be pressure as all these fishes are living in this one small habitat. And the area is becoming smaller because the climate is going to become warmer. So the internal seaways begin to desiccate. And so those aquatic environments have increased in diversity, as we talked about. And remember that in the Silurian, there's all this brand new space. So there's new land and new ecological niches that are going to be able to fill. And so that's the reasons why we see these amphibians go to land. So there's kind of like there's overcrowding, and like why not try it? And so with the development of the lungfish, they're able to move onto land. So, so interesting things are going to happen then, right? So as we're moving amphibians onto land, we're moving into a different ecological niche. So we're really thinking about how Kingdom Animalia and the vertebrates are going to develop on land, starting with the amphibian record. So my question to you then is, what's going to happen next? So we're in the Devonian, and we've developed the age of fishes, and we have a top predator called the placoderm, and our oceans are doing well, and now we're moving on to land with the amphibians. What's going to happen? Can you guess it? Yeah, a mass extinction is going to happen. A mass extinction is going to happen, and it's going to happen because of a glacial cycle. So you're probably thinking, what in the world? We finally developed all these cool phylums of chordata, these vertebrates. We've got things going on to land. Why do we have to end in a mass extinction? All the things come to an end. Sorry, folks. It's going to be the end of the placoderm. So we only see the placoderm in the fossil record for like 30 million years. I know, it sucks because he's one of the coolest. So we go into this Devonian glacial cycle. My question to you is why? And the reason is obvious. Did you guess it? There's 3 reasons. So the first thing is that, remember in the Silurian, we developed all of that plant life for the very first time. Kingdom Fungi and Kingdom Plantae, non-vascular, vascular plants. What do plants do? Photosynthesis. And we love that they do photosynthesis, right? So photosynthesis means that they take in carbon dioxide and water and they respire oxygen. But they are taking in carbon dioxide at such a rate that is what? Going to cool the planet. Because carbon dioxide is a greenhouse gas, right? So if you have an abundance of it, the planet's going to be warm. If you reduce that signature, the planet begins to cool. And so it is the presence of that life above sea level, the Kingdom Plantae and the Kingdom Fungi, that are going to turn us into the late Devonian glacial cycle. The next thing that happens is, because we have, for the very first time, bedrock exposed at the Earth's surface, we're going to go through this process of chemical weathering. And this is kind of outside the scope of an introductory class, but the idea is that if you have, like limestone, for example, if you have limestone that's exposed at the surface and you have rain that's naturally acidic, you can go through and produce carbonic acid, and in that process you're using carbon dioxide. So when you're breaking down the soil and the bedrock, you're using carbon dioxide, so you're taking it out of the atmosphere. And although we have introduced amphibians to land, they're not abundant yet. So this is kind of like the first knack of them like moving onto land. And so amphibians are going to take in oxygen and respire carbon dioxide, but it's just not enough to balance what we've created in the Silurian. So I know it's sad, but we are in a mass extinction as we conclude the Devonian. So I'm going to leave you here with the fact that the placoderms are no more, but it's not that large of a mass extinction. That's the good news. So it's like low scale devastation on the planet. Most everything's going to rebound. So I'm going to leave you with that for now. You've been a wonderful audience, and I'm going to post this couple of videos about ichthyostega and duckliostasis for you to check out. They're really cool. See you later.